What if I told you there's a potential second Earth just over 4 light years away? An alien world, possibly brimming with life, waiting to be discovered. This is the story of Alpha Centauri, our closest stellar neighbor, and the exciting possibility of Earth 2.0. What secrets does Proxima B hold? And could it truly harbor life? Stars from Alpha Centauri exhibit strange and mysterious behaviors. So what are the biggest challenges we face in exploring these alien worlds? And most importantly, are we on the verge of making interstellar travel a reality? Our journey to understand Alpha Centauri begins with its discovery. How did astronomers first identify these stars? The story takes us back to 1839, when Scottish astronomer Thomas Henderson made the groundbreaking discovery of Alpha Centauri A and B. Using meticulous calculations, Henderson determined their distance from Earth, marking them as our nearest stellar neighbors. Then, in 1915, the astronomer Robert Innes identified a faint red star nearby, Proxima Centauri. This discovery was monumental, as it meant that the closest star to our solar system wasn't just a distant solitary point of light, but part of a complex and intriguing stellar system. The Alpha Centauri system is composed of 3 stars, each with unique characteristics. Alpha Centauri A, a yellow dwarf, is remarkably similar to our own Sun. It shares a comparable size, temperature, and brightness, making it a point of interest for scientists seeking habitable planets. Alpha Centauri B, on the other hand, is an orange dwarf. Slightly smaller and cooler than Alpha Centauri A, it complements its companion star, forming a binary system. The dance of these 2 stars around a common center of mass is a celestial ballet that has fascinated astronomers for decades. And then there's Proxima Centauri, the smallest and faintest of the 3. As a red dwarf, Proxima Centauri emits less light and heat, but it's also known for its frequent and intense solar flares. These outbursts can have dramatic effects on the planets within its habitable zone. Scientists began to wonder if such a volatile environment could still support life. Why is the Alpha Centauri system so significant to us? At just over 4 light years away, it's our closest stellar neighbor. This proximity makes Alpha Centauri a prime target for study and potential exploration. But what does being close in astronomical terms really mean? To put it into perspective, light from Alpha Centauri takes just over 4 years to reach us. This may seem distant, but in the grand scale of the universe, it's practically next door. The short distance allows astronomers to observe these stars in great detail and speculate about the planets that might orbit them. The significance of the Alpha Centauri system extends beyond mere proximity. It represents the best opportunity for humanity to find habitable exoplanets within our reach. Scientists believe that if we can develop the technology to travel to Alpha Centauri, we might discover an Earth-like planet that could one day be a new home for humanity. If you're liking the video so far, you should consider subscribing to the channel and help us create better content and reach more explorers out there. Now back to the video. The discovery of Proxima B was a significant milestone in the search for exoplanets. This journey began with the radial velocity method, a technique that measures the slight wobbles in a star's movement caused by the gravitational pull of an orbiting planet. This method, also known as Doppler spectroscopy, has been instrumental in detecting many exoplanets, including Proxima B. In 2016, astronomers using the European Southern Observatory's HARPS, High-Accuracy Radial Velocity Planet Searcher, detected these minute shifts in Proxima Centauri's light spectrum. By analyzing the data, scientists concluded that a planet was orbiting the star every 11.2 days. This method not only revealed the presence of Proxima B, but also provided crucial information about its mass and orbit. Proxima B is a rocky planet with a mass about 1.17 times that of Earth, making it slightly larger and more massive. It orbits its parent star, Proxima Centauri, at a distance of approximately 0.05 astronomical units, or roughly 7.5 million kilometers. This close orbit places Proxima B squarely within the star's habitable zone, the region where conditions might be just right for liquid water to exist on the planet's surface. The concept of the habitable zone is crucial when considering a planet's potential to support life. For Proxima B, Its location in this zone means it receives enough stellar radiation to possibly maintain liquid water, a key ingredient for life as we understand it. However, its proximity to Proxima Centauri presents unique challenges. The planet completes an orbit every 11.2 Earth days, resulting in a very short year and a strong gravitational interaction with its star. Proxima B is likely tidally locked, meaning one side of the planet perpetually faces the star, while the other side remains in darkness. This creates extreme temperature differences and potentially harsh environmental conditions. Despite these challenges, the potential for Proxima B to host life remains an exciting possibility. The discovery of the planet was met with great enthusiasm and speculation. Scientists and the general public alike were captivated by the idea of a potentially habitable planet in our closest stellar neighbor. The initial excitement stemmed from the planet's location in the habitable zone and its Earth-like characteristics. Early studies speculated about the possibility of liquid water on Proxima B's surface. If the planet possesses an atmosphere similar to Earth's, it could support a range of life forms. The scientific community eagerly began modeling Proxima B's climate and potential biosphere, considering various scenarios under which life might exist. However, the harsh realities of Proxima Centauri's environment tempered some of this excitement. Proxima Centauri is a red dwarf star known for its frequent and intense solar flares. These flares can emit vast amounts of radiation, potentially stripping away any atmosphere on Proxima B and bombarding its surface with harmful rays. This raised questions about the planet's habitability and the survival of any potential life forms. Despite these challenges, scientists have not given up on Proxima B. Research continues to explore how life might adapt to such extreme conditions. For instance, on Earth, extremophiles thrive in some of the most inhospitable environments, from deep-sea hydrothermal vents to acidic hot springs. Could similar organisms exist on Proxima B? One of the most significant challenges to habitability on Proxima B is the intense stellar activity of its host star, Proxima Centauri. Red dwarf stars like Proxima Centauri are known for their frequent and powerful stellar flares. These flares release bursts of ultraviolet and X-ray radiation that can have severe consequences for any nearby planets. Proxima Centauri's radiation bursts are far more intense than those from our Sun. In 2017, a particularly strong flare from Proxima Centauri increased the star's brightness by a factor of 1,000 over a span of just 10 seconds. Such events can strip away a planet's atmosphere, particularly if the planet is as close to the star as Proxima B is. Without an atmosphere, the surface of Proxima B would be exposed to harmful radiation, making it extremely challenging for life to survive. The constant bombardment of radiation also affects the potential for liquid water on Proxima B. High-energy particles from these flares can cause water molecules to break apart into hydrogen and oxygen. The lightweight hydrogen can then escape into space, leaving the planet dry and barren. This stellar activity presents a daunting hurdle for the possibility of life on Proxima B, but it is not the only challenge the planet faces. Despite the harsh radiation environment, scientists are still hopeful about the possibility of an atmosphere on Proxima B. An atmosphere could provide a shield against radiation, as well as the potential for liquid water, which is essential for life as we know it. But does Proxima B have an atmosphere? And if so, what is it like? Several factors contribute to the potential for an atmosphere on Proxima B. The planet's mass suggests it could hold on to an atmosphere, and its location in the habitable zone means it might have the right temperature range for liquid water. However, the continuous stellar flares from Proxima Centauri could strip away the atmosphere over time. If Proxima B does have an atmosphere, it would need to be replenished somehow, perhaps through volcanic activity or comet impacts. The presence of liquid water depends heavily on the atmosphere's ability to retain heat. A thick atmosphere with greenhouse gases like carbon dioxide could trap heat and allow for stable liquid water on the surface. Conversely, a thin atmosphere would struggle to maintain liquid water, especially given the extreme temperature variations between the day and night sides of the planet. Observations from telescopes and future space missions aim to detect signs of an atmosphere around Proxima B. Instruments that can analyze the planet's light spectrum may reveal the composition of any existing atmosphere, providing crucial clues about its potential to support life. Another major challenge to habitability on Proxima B is its likely tidal locking. Tidal locking occurs when a planet's rotation period matches its orbital period, causing one side of the planet to always face the star, while the other side remains in perpetual darkness. This synchronous rotation has significant implications for Proxima B's climate and habitability. The day side would experience constant daylight and intense heat, while the night side would be in continuous darkness and extreme cold. This stark contrast could create a hostile environment, with a narrow strip of twilight, or the Terminator line, being the only region where temperatures might be moderate enough to support life. The climate dynamics of a tidally locked planet are complex. The constant heating on the day side could cause atmospheric circulation patterns that redistribute heat to the night side, potentially creating a more stable climate. However, the effectiveness of this heat distribution depends on the thickness and composition of the atmosphere. Without a substantial atmosphere, the temperature differences could be too extreme for life to exist. Scientists use advanced climate models to simulate these conditions and explore the potential habitability of Proxima B. Understanding how heat and weather patterns behave on a tidally locked planet can provide insights into whether life could adapt to such an environment. These models are crucial as they guide future observations and missions aimed at unraveling the mysteries of Proxima B. While Proxima B has garnered significant attention due to its location in the habitable zone, it's not the only planet in the Proxima Centauri system. In 2020, astronomers confirmed the existence of Proxima C, a super-Earth with a mass about 7 times that of our planet. Proxima C orbits much farther from its star than Proxima B, with an orbital period of approximately 5.2 years. Proxima C's distance from its host star places it well outside the habitable zone, in a region where liquid water is unlikely to exist. However, its discovery is significant because it demonstrates the complexity and richness of the Proxima Centauri system. The detection of Proxima C was made using the radial velocity method, the same technique used to discover Proxima B, highlighting the effectiveness of this approach in finding exoplanets. To truly understand the Proxima Centauri system, we need more than just telescopic observations from Earth. This is where future missions come into play. One of the most ambitious projects currently in development is Breakthrough Starshot, a mission designed to send tiny, lightweight spacecraft to Alpha Centauri at a fraction of the speed of light. Breakthrough Starshot, announced in 2016 by Yuri Milner and Stephen Hawking, aims to develop and launch a fleet of nanocraft propelled by powerful ground-based lasers. These spacecraft, known as starships, would travel at about 20% of the speed of light, reaching the Alpha Centauri system in just over 20 years. Once there, they would capture images and collect data, sending it back to Earth. The success of Breakthrough Starshot relies on overcoming several significant technological challenges. These include developing lasers powerful enough to propel the spacecraft, creating durable nanocraft that can withstand the harsh conditions of interstellar space, and establishing communication systems that can transmit data across 4.24 light-years. In addition to Breakthrough Starshot, other missions and initiatives are being proposed to explore the Alpha Centauri system. NASA's Jet Propulsion Laboratory is investigating concepts for interstellar probes that could reach our nearest star neighbors. The European Space Agency is also exploring potential missions that could complement the efforts of Breakthrough Starshot. These missions represent the next frontier in space exploration, pushing the boundaries of our technology and knowledge. They hold the promise of providing unprecedented insights into the Proxima Centauri system and its potential for habitability. To send spacecraft to Proxima Centauri and beyond, we need advancements in propulsion, power generation, and communication. Traditional chemical rockets, like those used to send humans to the Moon or rovers to Mars, are not feasible for interstellar travel due to their limited speed and fuel requirements. Solar panels are ineffective in the darkness of interstellar space, so alternative power sources, such as nuclear batteries or advanced energy harvesting techniques, are being explored. Communication is another critical hurdle. Transmitting data across light years requires highly sensitive receivers and powerful transmitters. Scientists are developing new communication protocols and technologies to ensure that data from interstellar probes can be reliably sent back to Earth. Radiation protection is also a major concern. Spacecraft traveling at high speeds through interstellar space will encounter cosmic rays and other forms of high-energy radiation. Developing materials and designs that can shield sensitive electronics and instruments from this radiation is essential. The cumulative advancements in these areas will not only enable missions to Proxima Centauri, but also pave the way for future exploration of other star systems. Each technological breakthrough brings us closer to realizing the dream of interstellar travel and understanding our place in the cosmos. On Earth, life thrives in some of the most extreme environments imaginable, from the scalding hot vents on the ocean floor to the frigid ice caps of Antarctica. These organisms, known as extremophiles, have adapted to survive in conditions previously thought to be uninhabitable. For instance, the tardigrade, often called a water bear, can endure radiation, extreme temperatures, and even the vacuum of space. The study of extremophiles provides valuable insights into the potential for life on other planets, especially those with harsh environments. If life can persist in the acidic waters of Yellowstone's hot springs or the crushing pressures of the deep ocean, it might also exist in the extreme conditions of exoplanets like Proxima B. The possibility that microorganisms could survive under the surface of Mars, in the ice-covered oceans of Europa, or in the sulfuric clouds of Venus is not as far-fetched as it once seemed. Research on extremophiles has guided scientists in identifying biosignatures, chemical indicators of life that could be detectable in the atmospheres or surfaces of distant planets. For example, the presence of methane on Mars has sparked interest because on Earth, a significant amount of methane is produced by biological processes. Similarly, the discovery of phosphine in the clouds of Venus has led to speculation about microbial life. Another parallel effort focuses on finding intelligent extraterrestrial life. The search for extraterrestrial intelligence, SETI, has been listening for signals from advanced civilizations since the 1960s. Using radio telescopes, scientists scan the skies for non-random signals that could indicate the presence of technologically advanced aliens. One of the most famous projects is the SETI Institute's Allen Telescope Array in California, which continuously monitors thousands of star systems. Another initiative, Breakthrough Listen, funded by billionaire Yuri Milner, aims to scan 1 million stars and 100 nearby galaxies over 10 years. This project utilizes some of the world's largest radio telescopes, such as the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia. SETI researchers are also expanding their search to include optical signals, such as laser pulses, which could be sent by advanced civilizations. These efforts are based on the assumption that if we can conceive of these methods, other intelligent beings might have already developed and used them. Despite decades of searching, no definitive signals have been found yet. However, the vastness of space and the limitations of our technology mean that we have only just begun to scratch the surface. The discovery of an intelligent signal would be one of the most profound events in human history, fundamentally altering our understanding of our place in the universe. The discovery of life beyond Earth would not only be a scientific breakthrough, but also a profound philosophical and ethical milestone. What would it mean for humanity if we found microbial life on Mars or intelligent civilizations in distant star systems? Philosophically, the confirmation of extraterrestrial life would challenge many of our fundamental beliefs about life's uniqueness and the place of humanity in the cosmos. Religions and worldviews might need to adapt to incorporate this new understanding, potentially leading to both spiritual and existential reflections. Ethically, we would face significant questions about our responsibility towards extraterrestrial life. If we discover microbial life on Mars, should we prioritize its protection over our exploration efforts? The concept of planetary protection, which aims to prevent contamination of both Earth and other worlds, would become even more critical. Moreover, if we detect intelligent life, how should we approach communication? The potential risks and benefits of contacting an advanced civilization are subjects of intense debate. Some scientists argue that we should listen, but not transmit, to avoid revealing our presence to potentially hostile beings. Others believe that establishing contact could lead to tremendous advances in knowledge and technology. These considerations extend to future missions and the colonization of other planets. As we plan for human settlement on Mars or the moons of Jupiter and Saturn, we must consider the potential impact on any existing life forms and the ethical implications of our expansion into the cosmos. We are constantly finding more and more solar systems where planets might have the conditions to support life. On the video appearing on your screen, we go deeper into the discoveries of the record-breaking exoplanet finder Kepler telescope. What new mysteries is humanity going to uncover next? Leave it here in the comments and take the opportunity to like the video and subscribe to the channel for more videos like this.